running linear models. So what we will cover here, we'll have a brief overview of linear models, very brief because I'm not a statistician, that's Rodolfo. And we're not here to study linear regressions. We're just here to figure out how to use them in R. What type of data goes into these models, how to use the LM function to run linear models, how to evaluate and plot your model, and how to use predict to predict with your model. So here are our learning objectives: working with continuous data in R, using the LM to fit our model, using ggplot and ggfortify to plot our model and explore it and check it, and then use predict to predict. So that's basically what you will learn. So with linear models, we're going to do linear regression. We just want to give out a shout out to ANOVA. ANOVA is basically linear regression for categorical data instead of continuous data. And multiple regressions, which is basically with multiple predictors instead of just a single predictors that this is what we will use. The data that we will use, perhaps you've seen that before. Very, very clean and simple data sets. We'll use empty cars. That's car data. We'll use it for demo. And faithful, which is old faithful eruption and visitation. That would be our practice data. If you have your own data and you want to try it, go for it. Not sure this is the right venue for it, but if you want to try and run stuff on your own data, let's go for it. I'm here. So let's move to the data, to the manual, and let's see how we pull the data and understand why linear regressions. Let's see. Great. What are you seeing on Zoom, by the way? You're seeing this? Okay, cool. All right. So let me just zoom in. Okay. So again, we already mentioned that. Here's our data. So this is what I want you guys to do. I want you to run this data. Just means we are importing the data, and empty cars is the data that we'll work with. And let's explore empty cars with head and structure, which I'm assuming this is, you guys have already used that yesterday? Yeah. Yeah? Yeah. Okay, good. Did you use empty cars as data or no? But which one? Oh, the penguins one? I wasn't even aware that there is a penguins one. I know Iris. That's the flower one. Oh, interesting.
One big depth, the wing size.
Oh, I know.
There were 3 types.
First time I've heard about it. Okay, so I want you guys to run this, empty cars, and yeah, structure. Okay, you guys got it? Okay, so you can see that we have multiple columns here, okay? This is data from 1974, so very, very accurate, very current, okay? Motor Trend magazine, 32 cars with 11 measurements. The key value that we will use here, MPG, miles per gallon for fuel efficiency, weight in thousands of pounds, HP is horsepower, and CIL is number of cylinders. So let's load the other one. So I want you guys to load the second one, data for faithful, and let's run structure and head for faithful. Okay, so you guys got it? Okay, so the question that we'll try and answer using our practice data is, does a car weight predict its fuel efficiency, and should we care about it since we're all going to be driving electric soon? And what we're going to use with Faithful, which, by the way, 272 observation of eruption behaviors. The variables we have eruptions and waiting. So waiting time and eruption time, waiting between eruption duration and waiting between eruptions. Can we predict how long an eruption will last based on the waiting time between eruptions? In case you ever plan a trip for Yellowstone, because this is like measurements of the Old Faithful Geyser in Yellowstone National Park. Okay. Why do we want to use these data sets? They're really, really clean. They have a strong linear relationship, continuous variables, easy to understand the context, and they're built into R. Can you use your own? As I mentioned, can try. Not sure this is the right place though. Part one of our exercise is exploring our data. Okay, exploring our data. With linear model, basically what we want to see is if there is a linear relationship between X and Y. Before we use our linear model, because let me tell you, models accept whatever you give them and they don't ask questions. Okay, so they don't care if there is a linear relationship, they will explain it. You want to understand your data and you want to make sure that there is a reason for you to actually use a linear model. Okay, so before you fit your model to your data, you should always explore it first. This is called exploratory data analysis. So basically what we're doing right now is exploratory data analysis. One great book, Understanding Exploratory Data Analysis, is Numerical Ecology with R, second edition. It sounds like it's very ecology related, but let me tell you, gene expression, whatever, they all use the same ways for data exploration. So I think it's worthwhile, whoever you are, read this book. Yeah, warning, it's in Franglish. It was written by some people from Quebec, and you can definitely read the French accent there. Okay. Okay, so before we do that, let me tell you what I mean by exploring your data, right? Data should always be explored. It tells you if your model assumptions are met, if cleanup is needed, or if you have missing values. Here is a simple plot of how we explore our data, right? Miles per gallon, weight, and we can see it's very telling. We have linear relationship. Looks like we have some sort of a linear relationship in our data between weight and miles per gallon. Okay, so that tells us, okay, everything is cool. So let's move to our manual and see how we do that. Okay, so you already loaded the ggplot package, so you don't have to load it, but we want to plot our weight versus miles per gallon. Okay, so here is how we do it. We use ggplot. We define what we're using, empty cars. The x-axis, the y-axis, MPG. We're doing geom point. That's a scatter plot. We're just defining size is 3 and color is brown because why not? And these are just the labels that I put in for the title and for the X and Y axis. Feel free to change those. And the theme, black and white, and then the base size for the font is 14. That's basically what it means. Okay, so I want you guys to see if you can run it. Just copy, see if you can run it, because you will have to do that for Faithful soon. Okay. Good, you managed to run it? Did you get the figure? Yeah. Get the figure? Okay. So as we can see, again, that's the figure in the presentation. Not surprising, exploratory analysis. What it shows us is that heavier cars, which is here, right? This is the weight, have terrible fuel efficiency. That's what it shows us. Heavier cars, terrible fuel efficiency. Lighter cars, great fuel efficiency. Makes me feel really good for my Kia Rio. Okay, right, so, but we can also see that the relationship seems linear. It seems that we have a relationship that is based on addition or subtraction between those two, right? So I want to remind you, no biologists, this is math. It's very scary. I understand. I feel you guys. I'm also a biologist. But this is how we represent linear models, right? Y equals AX plus B. So we definitely see that if this is our angle of the, the line, right, the slope of the line, this is by how much we're growing, okay? So we're basically X plus B will tell us what Y is, okay? And we can see that we definitely have a relationship that seems to be growing or subtracting, right? When we subtract weight, we grow the efficiency by a factor that seems to correlate with it. Okay, so the next step, now that we have kind of like confirmed our suspicion that there is a relationship, we want to try and truly see if there is a linear correlation. And so we are going to use, we're going to test for correlation. We're going to do Pearson correlation, right? And the Pearson correlation basically assumes a linear relationship between two variables. So we can safely use Pearson here because we explored our data and we have a reason to believe that there is linear relationship. Does that make sense to you guys? Okay, so we're testing for Pearson correlation here using core. Core is another function, and here is the argument that it gets. Factor number 1 and factor number 2, and it tests the correlation between both of them, okay? And here are our correlation value, and we are printing them, okay? Also rounding it to just 3 decimal points, okay? And we see that we have a pretty strong correlation, minus roughly 0.87. Could have just rounded it up to 2 instead of 3. Never mind. Okay, so minus about 0.87. So that tells you that there is a very strong correlation that's negative, right? When we increase weight, we decrease fuel efficiency. When we decrease weight, we increase fuel efficiency. Does that make sense to you guys? So that's what we're doing. So I want you guys, again, to take this code, run it, and see that you're getting it. And once you got it, what I want you to do is I want you to then do the same thing, create a scatter plot. Don't really care about labels and titles, so don't worry about that. I mean, you can always modify mine, it's fine. And we want to calculate the correlation between those two. And what do you observe? Is there a correlation between the two? Not the correlation.
The last one, yeah.
Yeah. Let me just take this code. Okay. Okay. So now what you want to do is you want to do the same thing but for phase 4. Okay. Yeah. So you only have 2 variables here: your options and waiting time. Right? Yes. Thanks. Yeah, Robin, I'm sorry if I'm butchering mathematical concepts here.
I'm a bigger fan of discrete math thing.
Yeah, well, yeah. So I'm a biologist. That's what we do.
Very linear. Yeah.
There's time between eruptions.
I mean, okay, and this is years,
Minutes.
minutes.
Yeah.
Oh, it's a geyser, not a volcano.
Yeah, it's a geyser. Right. Old Faithful, it's the most famous geyser in Yellowstone
Yeah.
because it's so predictable, right? And it's huge. Also, it's huge. It's a huge geyser. Yeah.
Where if the first batch is already wave C and erupting, and so it's really long lasting, but probably have to wait for a long time. Yeah.
Longer time,
Longer.
not super long, right? Like we're talking about like 90 minutes, 40 minutes, 90 minutes, right? So yeah. Okay. So I know David plotted. What about Yasmin? Plot?
Okay, yeah, no, before us. Okay, might be pretty zero.
Where? So, base and base zero, they're kind of like the same purpose, different version of the same function. One of them you have to specify your spacing, so in one of them you don't. So it's like, it doesn't really matter. But okay. Yeah, sometimes it really depends on when I press the enter on the autocomplete, if it autocompletes print zero or if it autocompletes print, because they are pretty interchangeable. It's just that print zero is a little bit more robust to errors. Yeah, it's less, yeah. But both of them are pretty good.
For base size, you can use that. You can search the underscore TLD. So you have it.
Right, that looks like you ran it. Okay, very good. Yeah, that looks good. Did you run the correlation?
Correlation, yeah.
Okay, so run the correlation.
Oh, I the true and choose the data set.
When?
And how did you run the correlation? I didn't go.
You took the cars.
Perfect. So there is a very strong correlation between grading and eruption.
So you need to choose what data set you. Yeah. So right.
Yeah. Good, good, good.
Yeah.
So it should be.
All right, did we all get it? Did we all get to core? Did we all do the core test? Good? How much did you get, Yasmin?
901.
Did you all get that?
Yeah.
Good. All right, so okay. Looks like we have good evidence for linear relationship. Okay? That means that we can now try to take our data and fit it to a linear model. What do we mean by fit it to a linear model? And Robin, please plug your ears. Okay. Okay. What do we mean by that? Okay, so a linear model basically predicts y for values of x. That's what a linear model tells you. X equals 5, therefore y equals minus 10. X equals 10, therefore y equals minus 15. Okay, that's what it will tell you. And this is, if you remember your very basic 8th grade algebra, this is what you get here. When you will, if you know what B is, and you know what A is, then for every value of X, we can get Y, right? And so when we're fitting a linear model, basically what we're asking is, hey, function LM, can you find my A and can you find my B, please? So that when I put X, I will know what Y is. That's basically what it means. Give me my equation and tell me what A and B are, so I don't have to do it by hand. Okay, so that's basically what it does. So now let's look at how we use LM to do it. So again, remember, here is our model. Y equals AX plus B. If we know A and we know B, then we can get Y for every value of X. Okay? So if we're looking at this, X is the variable X, or oftentimes it will be referred to as the predictor of Y. A is a constant. That the slope in which the value of X changes, or how fast does X need to grow in order to predict Y. Okay, B, also a constant. B is the value of Y when X equals 0, therefore AX will also equal 0. Okay, so if AX also equals 0, then that basically just gives me the value of Y. Okay, so the value of Y when X equals 0, it is referred to as the intercept, since it intercepts the y-axis. I want to remind you, y-axis is X equals 0. Okay? So this is in contrast to models like exponential, where things grow by multiplication, as we can see here. Great. So now let's look at the function LM. Okay, this is our LM function. It's a function from the stats package, which you don't have to install because it comes straight with R when you install it. And it uses the formula interface where we have Y something X. Okay, note that here we don't use comma. And also we don't have to put anything in brackets because we specify our data. So that's how we can use it. Okay, so Y represents is the response variable, what we're trying to predict. Okay, the squiggly line basically means is modeled by or depends on. So y is modeled by x. That's basically x, by my predictor variable. That's the formula. Okay? You don't necessarily need to remember this. That the only thing you need to remember is here, this thing. So here is our model for cars. We're going to assign it a variable, linear model, LM. MPG is my y, right? Response variable is modeled by weight, which is my predictor variable. Oh, but where am I taking MPG and WT? Oh, data equals empty cars. That's my data. Does that make sense to you guys? Okay. And then we're going to view it. And look, lo and behold, my intercept, 37.3-ish. Okay, that's where, that's what happens. That's my B. My slope, my A, WT, is minus 5.344 or minus 5.3. Okay, minus 5.3. So basically what it tells me is MPG, which is my Y, equals minus 5.344 weight or WT plus my intercept 37.5. So this is the A, this is the X, and this is the B. You guys understand that? There we go. Okay, so the intercept, right? This is it. Predicts MPG when weight equals 0, which is obviously not meaningful because there isn't a car that weighs 0 pounds yet, but necessarily mathematically, okay, it's necessary from a mathematical perspective. Here is our slope. So for every 1,000 pounds increase in weight, this is right, because that's our unit. MPG decreases by this ish, or by this fast. Okay, so I want you guys to run it because afterward we'll run it on Faithful soon. So I want you guys to copy it and run it and see that you get it. Good.
Yes.
Okay, good. All right. So now we have our model. We got the output, right? If we click model cars, we'll get the output. We can also use summary. Okay, we can use summary. That's a function to get a summary of our model, right? It's possible to run summary function on our model to get a detailed summary of the necessary information to evaluate our model, our model's goodness and our model's accuracy. So let's see what we're getting here. So we're running summary. The first thing that it tells us, this is really cool. It tells us this is the function you called, right? So if we're thinking reproducibility, there we go. It captures what function you called. That's really great. Then we get our residuals. Then we get our coefficients and our significant level, and so on and so forth. So as you can see, summary returns a lot of information. Yeah.
Get all the information from summary.
You can't get all the information from summary. You run the summary on the object that you ran LM on. Okay, so that's a great question. It is, that's a great question. Okay, look at what we're running summary on. We're running it on model cars. So you're running summary on your model. Okay, so you ran LM, you got model, and now you're summarizing the information in your model. Make sense?
Yeah.
Great question. Okay, so yeah, so let's try and figure out what are key things to look at. First thing, we need to look at our coefficients. Okay, we have the estimate, which is the intercept and slope value, right? We have it here. In estimate, we have the intercept and slope value. Okay, standard error, the uncertainty in estimation, the smaller, the better. So we have our error here. Okay, t-value and probability, whatever, those are statistical. Basically, that's a p-value, statistical significance. The p-value of 0.05 is considered significant in most biological cases. And we want to note that statistical significance doesn't necessarily mean biological significance. It's just a statistical measurement. We need to always look at our data. Okay. And then we have our R-squared value. In this case, it's 0.75. Basically, what it means is weight explains 75% of the variation in values of MPG. Higher R-square, better model fit. It ranges between 0 and 1 or 0 and 100% if you multiply by 100. Hand wave explanation. Again, Robin, please plug your, okay. Hand wave explanation. This model predicts miles per gallon based on predictions of miles per gallon based on weight are on average 75% accurate. Okay, that's basically what it means. Let's imagine that this is a model that predicts flu outbreaks in the United States based on vaccination or whatever. Vaccination is a contentious topic these days, based on how much McDonald's you eat. Okay, then our model would be able to predict the probability or the likelihood of a flu outbreak based on how much McDonald's visitations there are with 75% accuracy on average, which is pretty good in public health, the way I understand it. It's pretty good. Okay. And then lastly, we have our p-value, which is pretty tiny. Right, it's like basically 0.10 decimal points 1, something. It's really small, extremely small. This relationship is statistically significant, so it is not due to random chance. So what does this mean in plain English, I hope? For every 1,000 pounds a car weighs more, we expect to get about 5.3 fewer miles per gallon. Weight explains 75% of why some cars are more fuel efficient than others. This relationship is highly statistically significant. Does that make sense to you guys? You guys all see it? Understand it? Good. Hopefully, no offense to any mathematician in the room. Okay, so now let's do the same thing, but for faithful with eruptions and weighting, right? So basically, we want to predict eruption time from waiting time, right? So waiting time should be our x here.
Waiting is X.
Yeah.
That word should have been for the, we did a bit of a graph.
It doesn't really matter. I mean, it could, but linear relationship is linear relationship, and it should work in reverse. It should work in reverse.
When you do the function goes to X and then Y.
Yx.
Y then X.
Y depends on x, right? Eruptions depend on waiting time. eruption duration depends on time between eruptions.
Remember how to use trees. Usually
There's nothing like changes the trees and the. So these.
yeah, these are also
So how do you use them?
That's it?
yeah. As long as
Override.
yeah, right here. Over here. Oh yeah, no, it's the previous. Oh, you have to run the. You need to run V4 just by itself.
How's that?
Going well.
You're using your experience running on your
Yeah. Good.
I think summarize is
Summary,
yeah.
the summary of the model?
Yeah.
Yeah, summary or whatever you call it. Faithful model, yeah. All right. So I see you guys are pretty much killing it. So what was did you guys all done? Are you guys all done? All right. So what was the slope that you guys got? 0.07. Yeah. So what does it mean? For every increase in eruption time, we increase our waiting time by 0.07 units of time. Ish, kind of. Yeah. What's the R square value? R squared value.
Minus 1.87?
No, should not be mine.
0.81.
Yeah, 0.81 should be.
0.81.
Yeah. Is that what you guys got? Well, yeah. Yeah.
Oh, yeah, it's 1.87.
No, I think that's the intercept, or no, that's the error rate we're doing.
Oh.
Yeah. 0.8115.
Okay, good. Okay. So how much of the variance are we explaining basically? 81%, 81, 82%. Okay. So if you think about it, it kind of like shows you why this geyser is called Old Faithful. Because even though we can predict waiting time based on eruption time, right? If eruption time, if eruption time is longer, waiting time would be longer. Okay, the variation isn't large. We're talking about 0.07, right? The variation isn't large, and there is a really strong linear relationship between them. Okay, is the relationship statistically significant? What's the p-value? No, it's not 2 point.
Yeah, it's significant. It's 2.2.
Ah,
60.
Oh, okay, that's it. Yeah, okay, sorry. It's like, yeah, I'm just used to like 0.60 zeros. It's like, okay, all right. Yeah, so very statistically significant. Okay, cool. we can also, if I can do that, we can also visualize our model, okay? When we're visualizing our model, ggplot is our friend. Why doesn't it show me here? Oh, I know why, okay. All right, so when we're visualizing our model, ggplot is a great tool to visualize models, not just linear models. geomsmooth is our friend here because geomsmooth has the ability to actually run LM, get your model, and plot the line that comes out from the equation, right? So here it is, weight multiplied by this plus 37.3 with the R square of this one. So that's what we would get. That's what we would get if we plot this equation, and we can see the variation of our actual data around the model here. Okay. So later on, when we use predict, we will see that our model is continuous data because we can basically get y for every x, even though we don't have a measurement for every value of x and y. Our model is continuous. We can do that. Okay. So now let's move to our manual and see how we do it. Okay, so we've already explored the relationship between MPG and weight, and with the scatter plot. If unlike me, you exercise a good practice, we've covered in previous model, and you assign plot to your global environment. You already called it as a variable. You can just use the plot and just add geomsmooth. But if you haven't assigned it to a variable, you will have to, just like me, practice poor coding practices and repeat yourself. Okay, so I'm repeating myself. I'm being verbose here just so you'll see what goes on. Okay, so we want to plot our model onto a graph so that we can evaluate, for example, how scattered are our measurements around the predicted values. Right now, you can understand why it's only 75% and not 100%. Okay. So, right. So note that so for us, what we'll do is we'll use geomsmooth. Note that geomsmooth can use LM, but it can also use other types of models. They don't have to be linear. So if you want like a polynomial model, then you can use that as well, right? And if you care. Okay, so here's what we're doing. Again, we are plotting our scatter plot. This time we're coloring it slightly different. And we're doing our geomsmooth, our method. What method of model that we want to use is LM, that's the linear models. We want to add standard error, and yeah, and then everything else doesn't really matter. The labels, we already know them. And so that would be what we're seeing here. Okay, here is our model graphed. The line is our model. The gray stuff, right? That's our the black line is our fitted regression line. The line goes through the quote unquote middle of the points, minimizing the overall distances between all points. Doesn't really matter. The gray shaded area is 95% confidence interval. So I said standard earlier. Sorry, that was a mistake. It's 95% confidence interval, kind of like the uncertainty around the line. And the points, those are our observed data. And again, what we see here is our expected values of y and our actual values of y. And we can see that we don't have 100% fit between our expected value of y based on our model and our actual measurement. Does that make sense to you guys? So again, that explains to us why our model is only, again, hand wave, only 75% accurate in predicting. There is variability around those values. Does it make sense to you guys? You see it? Okay, good. All right, so what I want you guys to do is run the same thing on faithful and see what you get.
Should the x-axis be weighting?
The same.
Same, yeah,
I mean, same as what you use for the model.
yeah.
Same as what you used for the model. The x and y axis should be the same as what you used for the model. So if you switched weighting and eruption, then yeah. We don't have any more schedule breaks, right? Good, because we have like 2 more sections and then we're done.
Yeah.
I don't think I will need to. Yeah. We'll see. Yeah, we'll see if maybe we'll do the summary exercise. Summary exercise might be a little bit extensive. Yeah.
Really, I'm doing, really, it's for time.
I think it's minutes.
Minutes.
Yeah.
Well, what would you visit? You visit, yes,
I've never been to Yellowstone. My brother's been all over the place to see those geology. So he goes to all like all the other parks, but I've mostly been around Alberta.
It's not that, it's like maybe like a 15-hour drive.
Okay.
So it's like a really nice.
Yeah.
There's a Montana. Like mine was.
Yeah, I just like the concept of like who goes there, right? But there used to be many volcanoes there, which I don't know because my brother, and he sent pictures and it's like, whoa,
Yeah.
Idaho's beautiful. Okay.
The most annoying drivers on the planet. Everybody's driving there like they're a couple years old.
Oh, okay.
Everyone drives like they're on the average.
Yellowstone then?
Wow.
For like camping or?
Yeah, for visiting and also was at a conference in like Sky. They the guys from like University of Wisconsin or and tour of Yellowstone. So these are like real events. It's amazing.
I wanna go to Nahanni National Park next summer.
Where's that? Is it like Yukon or Northwest?
Yeah.
It covers both. But you have to like float plane it and then backpack like crazy, so I'm trying to peer pressure my friends.
Yeah, so what, like you can Florida, you airplane?
Oh, I don't know, my brother knows some people, cause he works also like in Alaska and northern BC where they.
So those ones can fly for sure, that's the company, so Calgary based company.
We also have family friends who have like, they live in Alberta, but they have a hunting company where the helicopter people up to Alaska.
Yeah, but helicopter probably has to stop along the way to fuel and stuff like that, the range isn't like very huge. All right, we good? We got it? Let me check. I want to see what you guys got. Nice. Okay. So we visualized our model. Okay, we visualized our model. We checked. First of all, we checked our data. We explored our data. We saw that we don't have any missing values, that the relationship seems to be linear. The data is not categorical. And we tested for correlation and we saw that there was correlation and we fitted our model and we saw that the model is significant and the R square is relatively high. And then we plotted it with like the geom smooth, and we plotted our 95% confidence intervals, and we saw our model, and we saw how the data is centered around it and how much variability we might have based between the predicted and the actual values. And we saw that our model looks really, really well. But that's not enough. We also need to diagnose the model, because every model has an underbelly, and the underbelly for the model is the assumptions that it uses. Okay? For example, the assumption for ChatGPT is that you guys don't care about the output so long as it sounds convincing. Okay? That's the assumption. That's why it pumps out so much nonsense. Okay, so but the assumption for this model, the linear model, is that there is a linearity of our relationships between X and Y, which we've already kind of like demonstrated, that there is an independence of the observations, which is kind of like what it is. We know that we have independence of our observations, and that there is a normality and homoscedasticity of the residuals. What are all these? We'll talk about it in the manual. It's like very, very big names, but very simple concepts. And violations of any of these means that our model is unreliable, which means that we can or can't use it for predictions would depend on if we violate those assumptions. So let's move to the manual and see how we diagnose our model and what it actually means. All right, so again, here are, okay, so linear models makes the following key assumptions about your data, and if these are violated, your results may not be reliable. The first is, but first the basic definition, we'll use it a lot. Residuals, what are residuals? Residuals are part of the data that your model didn't explain. In other words, residuals are the difference between the predicted data and the actual measured data. Remember our black line and the dots around it? The fact that they all didn't align on the black line, so that distance between the dot and the black line, that's the residual, whatever. Right, for example, if a car's actual MPG is 22 and your model predicts it to be 20, the residual is 22 minus the predicted value, which is 2. That's it. That's what it means, okay? So key assumptions. Linearity, the relationship is actually linear. We already explored it. Independence. Observations are independent of each other. They are different car makes for empty cars. We have different car makes from different makers. Okay, we have different cars from different makers. They are independent of each other, okay? Think about if you can make the same assumption for the faithful data set. I think you can. Homoscedasticity, that's the variance of the residual is constant. We don't see kind of like what we call a funnel pattern in the residual versus a fitted plot. And normality, the residuals approximately are normally distributed. So did you guys already install GG Fortify earlier? Okay, so Yasmin, just do install packages GG Fortify and then load it. Load library GG Fortify. Okay.
And then try running library to choose. If it has to look at. Oh, so let's just do this. Yeah.
Yeah.
Okay, we good? All right. So GG45 package makes it really easy to create diagnostic plots for linear LM models. The test for assumptions 3 and 4. They actually test for a whole slew of other assumptions. We won't go into that. So it produces a lot of plots. We're only going to focus on 2, right? We will look for assumption 3, and we will, so basically plot residuals versus a fitted plot to test for assumption 3, and we'll do a QQ plot to test for assumption 4, which is the normality assumption. So we load our library, GG45, and we'll just do auto plot our model car. Which plots do we want? We only want plot number 1 and 2 in whatever it is that it's making. It doesn't really matter. Basically, 1 and 2 tells it to just do the residual versus fitted and QQ plot, okay? Number of columns that we want 2 columns. Instead of having them one stacked on top of each other, we want them like this, basically side by side. That's basically what it means. And size equals 2, that's the size of the dots. Okay, and as you can see, theme black and white, just like ggplot. Okay, autoplot, we do it. That's what we're looking at. So let's look at plot number 1, residuals versus fitted. Good, points are randomly scattered around a horizontal line at 0. Kind of looks like it. If we squint it the right way, kind of looks like it's randomly around the 0. Bad, curved pattern, which shows nonlinearity. Funnel shape, which is heteroscedasticity, and that would be represented by the blue line. They don't really follow the blue line. Maybe they follow this line. Anyway, we're going to pretend that everything is hunky-dory here and that they are all randomly distributed around this. And then the next one is the QQ plot. That's plot number 2. We can see it here. Here is our straight. If they're randomly distributed, they should run a 45-degree diagonal line. And that's kind of like what we're seeing, except for the ones towards the fringes, the ones towards the fringes. So generally, it looks good. Points fall roughly along the diagonal line. So this is our introductory analysis. So we can get by squinting and saying that things look good here. But I would really recommend, if your data is complex, that when you do these, you run it through someone who is a statistician, like Rodolfo. Yeah, so for now, we cannot we can feel free not to stress about, does it really around the 0 or not? But when you have your own actual data, consult a statistician. Yeah, that would be great. All right, so let's practice and use autoplot from GG45. Right, and then examine the residual versus fitted, any patterns that you see there, examine the QQ plot. Does it follow the line? Does this model meet the assumption? Can you assume data independence?
So you don't need to do the findings. Only one is your actual confidence in the model. Yeah, one was just so you can actually look at the code, but your model has.
Yeah.
Your model should be. What is that? I don't know.
It looks like it's more scattered around
Yeah.
But
this
what's the one with
than it is this.
You want the one with.
This looks
No, see, this is
very
the model.
normal distribution.
Good. Or the other.
All right.
No,
looks good.
What are these then?
No, not usually.
Need to look inside of it. Those probably are like the
Let me see. Yeah.
outliers.
This, that's what confuses all.
Oh, you're talking about.
It's something kind of.
Yeah, the board see these ones.
Okay, so now the.
Yeah, we can read that kind of like few help or read the tutorial, and they will probably tell you exactly how they calculate these outliers for kind of like the repeated versus kind of like actual observation.
Yeah.
And tell you exactly what, like how they kind of like decide what an outlier is.
Yeah.
Yeah, you got your thing.
You get the same for the Q2 plot, right? They'll highlight outlier there.
The things we have discussed.
No. So
Looks like that's what.
it looks like that looks pretty good. So it's kind of like randomly around this. They don't kind of like coalesce into like a funnel. Okay. All right. So that was pretty exciting, right? The model seems to be working well for everybody. The dots didn't kind of like coalesce towards like one kind of like value. So that was pretty good. Do you have like a linear model here? Like, is there a QQ plot shows normality? Yeah. Harry, what do you think?
I don't think so.
You don't think that the QQ plot shows normality?
But what would be?
So this is the QQ plot, and it shows diagonal line. That's pretty diagonally, right? You guys have a diagonal line.
Yeah.
So can we assume that we are okay with normality here? I would be really confident using that. If my data looked that good, I would be happy. This is, yeah, so you have normality. So can we assume that our model meets the assumptions then, based on those two graphs? Do we have the dots in our first graph all coalescing to kind of like from both ends, they're all coalescing to the same point? No, that looks good to me. Okay. Our QQ plot has a linear, kind of like the dots running along the diagonal, maybe except for the fringes a little bit. Yeah, that looks really good to me. So we can assume that we meet our assumptions. Now, can we assume that our data is independent? Can we assume that eruption 2 is independent of eruption 1? I think we can, because eruption 2 doesn't care if eruption 1 happened before. It just happens. It's kind of like a Markov chain. Just happens, right? There is no, it doesn't care if eruption 1 happened, and yeah. All right, so now comes the even more exciting part is, and again, the goal of our using LM is to try and predict, right? Every time we use a regression, the idea is we're trying to predict something, Okay, so the package stats has a predict function. Okay, but before we talk about it, let me just run through what it does. So models allow you to predict, again, in our case, we get y for a newly observed x. So let's say I have a car that I haven't observed when I constructed the model, okay? And I only know the weight. Based on the weight, if I put the weight in my model, I can get MPG, projected or predicted MPG. Does that make sense to you guys? Okay, I have like Mazda, whatever cars here. All of a sudden, I got like a European car, like a Fiat, okay? And so, but I only have the weight in pounds. And it's, let's say it's 5,000 pounds. Oh, I know it's kind of like around 10 miles per gallon. How do I know that? Because I can put 5 into my model and see what Y I get, what MPG I get. Does that make sense to you guys? So when we're saying predict, that's what predict does. But at the same time, that's also what Geom Smooth does when it outlines your model, right? So I want you to understand that in a sense, you already have predicted values with your model because you can run a line here and run a line here and see where do I land for every x for every value on the x-axis, where do I land on the y-axis along the lines. Make sense to you guys? Yeah, okay. Okay, but let's see how we can use predict so that we don't have to draw lines on our graph to get the value. Okay? All right. So the code below allows us to use predict to predict our value. Okay? So code below, I'm creating a data frame. Predict requires a data frame as an input argument for new data. And then I'm gonna feed it to the predict function, right? And note that I'm giving it new weight observations, and those weight observations, they fall within the range of our old observations, which were, if I remember, between 1,000, right? Between 1,000 and 5,000. That's where we had. Let's try and look at where we had our observations. So our observations were slightly above 5,000 and around, it's like, yeah, 1,500. So note that all of the new data that I'm creating here, all the new weights that I'm creating here, are in the range of our old observations. So I'm going from 2.5 to 4,000 pounds. Okay, does it make sense to you guys? Okay, cool. Right, so I'm using data frame. Here's my column. And again, the reason why I'm using a data frame specifically here is because predict requires you to have a data frame as an argument. If you would just give it a vector, or yeah, if you just give it a vector, it will crash. Okay. And note how I'm commenting everything. So good coding practices. So now I'm going to make the predictions. Here are my predictions. Predict. Here is my model. Here is my new data that I've created here. The intervals I want are confidence intervals. So 95% confidence intervals. Okay. So now what I'm going to do is I'm going to take my prediction and new car, and I'm just going to bind those two data frames. So cbind just means that I'm binding the columns of the new data frame. So I had this column from the old data frame and these ones from the new data frame. I'm just binding them together and I'm printing my results. And what it tells me is for 2.5 1,000 pounds, I'm predicting around 24 miles per gallon, right? So 2,500 pound car, the predicted MPG is around 24 miles per gallon, and confidence intervals between those ranges. And for here we have a 4,000 pound car. I'm predicting around 16 miles per gallon, and these are my confidence intervals. So the range the range here is 95% confident. So we are like 95% confident that the true where the true mean lies. Okay, so that's basically what we're doing. Okay, so this is how I'm using predict. Does it make sense to you guys? Okay, do you understand what I did here, or do you want me to break it down a little bit? Okay, which part do you need me to break down? The part after predict? Okay, so we've predicted our data. This is a data frame. The output, because the input here is a data frame, the output will be a data frame. So I have two data frames here, and I want to merge them into one data frame. Okay, so what I'm using is cbind, or if you guys used yesterday, call bind. I think that's what Tidyverse calls it. So what I'm saying is I'm taking my first data frame that only had this column, and I'm taking my second data frame that has 1, 2, 3 columns, and I'm gluing them together so that I'll have the first column from data frame number 1 and the rest of the columns from data frame number 2 from predictions. Does that make sense to you? Okay, two tables, because they both have the same number of rows, I can glue them together. Okay, so that's all I did. And then I printed it. And these are the values I've used here, right? 2.5, 3, 3.5, 4. Okay, those are the values I've used here. So those are the weights. This is the fitted value. Okay, so again, about 24 miles per gallon for this one, about 21 miles per gallon for this one, about 19 miles per gallon for this one, and about 16 miles per gallon for this one. Does that make sense to you guys? Okay, and lower interval, confidence interval, and upper confidence interval, 95% confidence. Okay, that's it. That's what we're getting. All right. So I want you guys to run this so that later on we can run it on Faithful. Okay, so let's have this so that we can run it on Faithful. You jumped that already?
Yeah. But I did run the other one.
Did you run the Faithful as well?
No, not yet. I will. I do that right now.
Okay.
It's because you want to use the one. So
Where?
because you put your consequence, right?
Yeah.
You don't need the first one should be your model.
There's two runs.
Yes.
That's the confidence interval, then I'll put if you do this one. Keep it higher.
If people.
And same thing.
People more.
57. 3.
Waiting more. You use price. Functions. Should you want to use like certain things? I use them.
But they didn't use that before, so why can't I use waiting time?
There you go.
Maybe this should be the other function, eruptions versus waiting. I'm sorry.
No, you know.
All right, so you ran it on Faithful as well already? Okay, good. So, so did you guys get predictions from Faithful? Okay, so what minutes did you use for Faithful? What value did you use for Faithful?
I use 50 to 90.
Okay, so that's within your range.
Yeah.
Okay, so what did you get for 50?
1.9 plus or
So
upper confidence interval is like 2.01 and lower with 1.79.
okay, so if we're using 50 minutes, basically what we're getting is about 1.9 minutes addition to our waiting time. What was your first number, Yasmin?
It was 15, 65, 80.
Okay, so for 65, what did you get?
3.4.
Okay, so what does it mean for us? That we would get about 3.04 minutes of additional waiting time. Okay. What about Harry? Give me your third one.
Yes.
Okay.
You. What was your question? Yeah.
So the third value.
This proof results. You still making results. Okay. Result rate.
So 80. What did you get for 80? How many minutes?
4.17.
4.17. Okay, so now we understand how we predict, how we use the predict in order to do that. Great. So now, now let's visualize our prediction. Okay, now let's visualize our prediction and see where our predictions fall on the graph. Okay, so you already heard my dry spiel. Right, I am reusing my code here. Again, the reason why I'm verbose in reusing my code is for you guys to see what I'm doing rather than just doing plot something plus geom, whatever. Okay, so here what we're going to do is we are going to feed the results variables as data to another scatter plot. So we already have our scatter plot, so we're going to do and use another scatter plot, but we're going to use our second data. So this is a great example. You guys asked me earlier in the workshop, why do I have to specify my data here and not in the geo? Now you're going to see why we have to specify the data in ggplot and not in the geom. Okay, so what we're going to do is we're going to have data that will feed to another scatter plot. That's our prediction data. And we're also going to use geom error bars to display the confidence intervals. Okay, so I want you guys to look at this. What do we have here? We are running our plot, so we've already done that. Okay, ggplot, in this case I'm using empty cars. Here is my x, which is weight. My y, what I'm predicting is mpg, miles per gallon. Geom point, we already done that. Okay, so we have our points for x and y. That's to plot our observation. The next one is geom smooth. Do you guys remember what geom smooth does? What does geom smooth do? What does it do? What does it plot? You're not a student. Linear regression, and what does it plot? No, like what do we get? The trend line. We get the trend line. Okay, we get the trend line. Note, I'm not stating data for any of them. Okay, empty cars is here. Geom point knows to use empty cars, knows what x and y to use. Same for geom smooth. It knows to use empty cars and it knows what x and y to use. Now, as my great comment here for my code, good coding practices states, we are going to add our prediction points, the points that we're predicting. Okay, so we're adding another point. We're adding those new points. Okay, note that here I am specifying new data. That's our results. Okay, those are our results. New data. Because I'm specifying new data, I have to specify new mapping coordinates. What are my coordinates for this data? X is weight and Y is my fit. Okay, where does it fit? Which is basically the equivalent of MPG. Okay, the same. And here's my fit, again, whatever. And now I have another geom error bar. For geom error bar, again, I can't just use empty cars because I need my error bars. So what am I using? I'm using results again. Because I'm using results and it's a different data point, it's a different data source than empty cars, I have to specify my mapping variables. What is the x and what's the y? So again, weight and fit. And here I want to show my error bars. What are my error bars? My y minimum is lower, so that's basically going to be fit plus lower, minus lower. My y maximum is fit plus upper. There we go. Okay, then we have the labels, then we print. then we print it. Okay, does that make sense to you guys? Do you guys want me to break it down again, or are you good? Okay, so when we're running this, right, and again, we want to remind ourselves that geom smooth using the formula yx, y depends on x, shows us our prediction. Look, I used green, I think, yeah, there we go, dark green, as the color for my predicted points. We can see our trend line right here. And not surprisingly, our trend line is our model. So we can see that our predicted points fall between right on our where geom smooth predicted they would. And we can see how our confidence intervals, not surprisingly, match the confidence intervals that geom smooth outputted. Okay, not surprisingly, the new points fell right on the regression line and the error bars fell right on the confidence intervals. This actually shows you the power of geom smooth at displaying continuous data and kind of like helping you understand where your predictions will fall. Okay, so we got new cars. We were able to predict their MPG with a certain degree of confidence. Okay, so what do we have here now? So we have some things to be aware of when we are doing our predictions. Again, if you noticed, all of our predictions were within range of our data. Okay, they were within range of our data. This is called interpolation. Okay, we are using something within our predicted data within our range. And this is usually referred to, regarded as a safe practice. If we're trying to predict outside our range, this is called extrapolation. Okay, it's called extrapolation. Not really, and it's considered like a not very, or risky. We have to be aware that there is a risk here, that if we're using range that we haven't used for our model, our predictions might be unreliable. So how many of you here have used pipettes? Okay, so for example, if you're using a P1000 pipette, that's the pipette for 1 microliter, okay? Sorry, 1 milliliter, okay? If I will go down to range, and like normally they go down all the way to 200 or 100, okay? If I'll go down to 100, I can already see that it's not very consistent with how much water or how much whatever it is it dishes out, right? The volume variations, I can already see that they would be much less reliable than somewhere in the middle of the range between 100 and 1000. And if I will go below 100 or above 1000, I already know that I can't trust that pipette for those values because they are outside the useful range, right? It's the same with those models. If we are extrapolating outside of our range of data, we need to be mindful that our model might not be accurate or might be even less accurate. Does that make sense to you guys? All right. So you already done that. Now let's do the visualizations. Now let's do the visualizations. Okay, I want you to create a visualization showing your original data point, your field regression line, and your new predicted points for 50, 65, 80, and 95. Want them to be different color points, and yeah, add the error bars as well. You want to have the error bars?
Anyways, there's other limits problem.
What are you having trouble with?
So see, choose the use of them.
Every farm is here.
Oh, they are there.
If you are small, wider, this is not safe. Just to make sure the corners are strong. Yeah, that's sure if you really things.
So they do what sizes. Size are overlapping this one. Maybe. These more like triangles, yeah, triangles, yeah, two. I'm on treasure. Sure.
Or maybe it's interesting.
Not this small.
Well, wait, you put it dark green.
Right. Anything that Congress meant. Maybe you could also increase the things to say.
Yeah.
This is the yeah.
Yeah.
Say that more problem. Yeah, that's small, but I mean, yeah, I guess I just have to see.
Well, then we'll put it. Then
You never.
Yeah, and is it similar to the other one going to get cars?
Sure. Just we get the.
It's not working. So is there anything missing?
Always see it.
Yes, this one is not working. The example didn't work to me. Yeah, so the example copy paste one and cars.
What was the error? Can you run it? Let's see what the error is.
So the lower values.
Error G point.
Showing what.
WT not find. Do you have WT? Which WT not find? Did you run?
So it's pressing on executing the name for the error.
No, no.
Okay.
Yeah, it's just that one was important about something. After that, since the beginning.
This one is like 1 6.
So let's look at the results.
Yeah.
So you have waiting, so you can change this to waiting, right? But because
Yeah.
you,
But this example not.
yeah, but you
ended up-
I understand, but you overrode it, right? But what you did here is you overrode results. And so you can't use waiting because you can't use WT because you overrode it. Okay, so you should have, when you did it, you should have renamed results
Okay, you can be
to something else.
off the error bar.
That way you don't override stuff.
Okay, so yeah, bit here.
So, yeah, but now you can write, you can do it with this.
Mhm.
So faithful doesn't have WT, so it has
Waiting.
waiting, so you change it to waiting.
This one is.
My email is exploding. Didn't answer emails all day.
I'm good now, it's an hour later and so. Busy man, yes.
I applied for an internal grant and it's about like taking EDF from Brazil and frequency for antibiotic resistance.
Just wait.
And me is really excited about bringing in water samples from Brazil, biohazard, whatever. They think it's interesting, but they're extremely reluctant to fund something that sounds so dangerous. So I have to explain to them that I'm not bringing water samples, I'm bringing DNA samples, and it's literally just like sending DNA sample for sequencing in paper. So if it makes them feel better, we'll do it through a courier and UPS can handle all the paperwork, which are it's literally sending DNA for sequencing.
That, I know our lab response, but I don't know the name of that, but there's like strong connections to your age and there's like full of data. For some reason, I'm not sure.
So you have to read it first.
Yeah, so when you name your column,
Then you have to load like the data.
because you want to get your columns.
You have to run it and then just more finals.
There's a lot of data.
Show people.
Well, this is waiting. So faithful is waiting, but your predictions use W.
It's not basic.
Or they will wait.
So,
Okay, just hold it. Okay, go back.
Yeah. Once you start analyzing, so it's not.
Still faithful. Faithful.
And so it's hard to say.
It's waiting to get options.
Maybe you're
Waiting to get options.
making.
Waiting to get options.
Second in the lab, they want to get once, and they'll only have.
Data is, I don't think it's
just slow things to history.
also is working. What try running is going to be the night of main of the eruptions of the Hatam or the sea.
Yeah.
And then our data,
Yeah.
constitute for that.
Yeah.
And then which one is results now, see the results now, page.
Yeah, there's packages, others you can solve asking pass and do analysis and sometimes see.
Oh, that's right.
But you need to know how.
But it brings us.
Yeah, also, or you can.
See is asking pass, and we don't have to it's this big. So it'll be similar, but probably it's not CSV, it'll pass.
For your joke one.
It's not editing like us just.
Your joke one for the.
Like college.
Because this is your prediction.
Yes, the options.
Yeah, it's how you fit.
And obviously there's some
Oh,
packages that
change
you
to.
and also has different parameters that you don't know how to have.
Yeah. Well, this one is also. Because this is your predicted why, you know.
Let me ask you.
Yeah.
I'm asking, what was the next type of application, about when we have this kind of thing. And just your scientist and see the genius, it looks like you're, we're trying to, it's CS overlapping with your favorite fossil fun. Sometimes it does that.
Size here, for example.
You can play around the sizes and see this with some few different functions. It's possible to get what the stress has QPCL data, like QPCL array. Yeah.
With this.
Yeah, because you change the shape as well.
Not with this specifically, you will probably have to work with some factor packages. What I would do is I would look into some of the other workshops that
You can see
Bioinformatics and Bioinformatics software kind of has online already. And I would assume some of them have overview of how to use bioinformatics packages, right? So for FastQ files, there are dedicated packages to work with FastQ files for quality control. And then for expression data, you can't use a linear model for expression data because there is no linear relationship. You will have to, they use different distributions and stuff like that, right? So you will have to work with EdgeRD, Seek, and they use binomial distribution to normalize data, whatever, never mind. Anyway, yeah, so this will be nice for you once you have a CSV and stuff, start plotting, but for actual gene expression data, you will need to work with like some bioinformatics packages. This is just very basic stuff. Okay, so we can yeah. All right, good. You got it. Good. You want to try and put error bars?
There are error.
Oh, they are. They're just super tiny.
Yeah.
They're really tiny.
The
Yeah.
size is maybe interesting.
Helps a lot. For example,
No, it's fine.
you know, use
It's fine.
functions.
Yeah. Yes. Yeah. Okay, guys. So looks like everybody's done. Everybody's predicted. Everybody got to plot their stuff. Okay. Again, let's do some honorable mentions here. Our honorable mention, ANOVA analysis variation uses the same LM function, but with categorical data. So if you ever need to run an ANOVA with LM, like for example, with the number of cylinders, which is a category, either you have 6 or you have 12 or you have 4, whatever it is, right? You can just do it here, and that would give you, it will know automatically to run an ANOVA model here. It's basically the same, okay? So you can do that, okay? So the key point here is if you want to do an ANOVA, you're using the same function, LM, but you're asking a different question. ANOVA asks, do group differ, instead of how does continuous variables relate to each other, or how do continuous variables relate to each other. Another one is multiple regression, right? So you can use multiple predictors for Y. So for example, not just weight, maybe also add horsepower. Maybe higher horsepower means lower MPG as well, right? Maybe it will help us explain our data better. Okay, so again, you're using a same function, different arguments, and you can run it, right? We won't cover it today, but R makes it easy. Just add predictors with the plus to the formula. So I think we are on time, right? Kind of like 5 minutes ahead of time. Okay, so this is it. This is what we cover. I have summary exercises if you want. You can, I will post the answer keys to the course website. Our key takeaways from this part is that linear regression models relationship between continuous variables using the LM function. Before we do anything, we always want to explore our data first, right? Scatter plot, correlation before modeling, so we know that we are not on shaky grounds. We want to interpret our output. Our coefficient tells you, coefficients tell you the relationship. For example, slope equals change in Y per unit X. R square tells you the model fit or percent variance explained, and p-values tell you the statistical significance. You also want to check your assumptions, and that's true for every model. You want to understand kind of like what is the underbelly, right? For example, if you're using a model for nucleotide substitution, and the assumption is that all types of mutation happens at equal rates, then you might be on shaky grounds here, because not all mutations happen at equal rates. For example, transitions are more frequent than transversions, okay? So might be on shaky grounds. So we always want to check what our assumption is, and we want to diagnose our model and make sure that our assumptions aren't violated. We want to use the predict function if we want to make predictions, but we want to beware extrapolations, okay? We want to keep things in the range in which we tested our model already, in which we used to generate the model. Think about it again, like a calibration curve. If you're within range of your calibration curve, probably good. If you're outside the range of your calibration curve, at your own risk. Visualization is key. Always plot your data, models, and predictions so that you can visualize them and look at them and make sure that they are all nice and as they should be. If you want additional resources, intro to R chapter on, or sub-chapter on linear models, that was the inspiration for this module. Really, really great resource. R for data science, chapter 23 talks a lot about basics, and Quick R has a good review of multiple regressions. Super helpful. That's all for today. That's all for today. I really hope you enjoyed it. I'm still here. If you have any questions, if you want me to review something, whatever it is, I'm still here.